Properties of determinant. Theorem 3.3. We have A here in n by n matrix, and theorem says if we interchange two rows of A, we interchange row I and the row J, any two rows, then the determinant of B is related to determinant of A, like so. A simple minus sign here. And if we scale the ith row of A by a scalar C, then the determinant of B is equal to C times determinant A. If we do row addition, we apply a row addition on A matrix to get B matrix, then A and B have the same determinant. And the last one, a very useful result, is that the determinant of the product matrix, EA, E is an elementary matrix, where E is an elementary matrix. Then the determinant of the product, EA, is equal to the product of the determinant, determinant E, determinant A. The proof of D is based on A and B and C. So if we have already shown ABC, then we can use the results to show D. Let's look at the proof of D first. Suppose A, B, C are true. When we interchange two rows, this is how determinants are related. When we do scaling, this is how the determinants are related. And when we do row addition, the determinant is not changed. Now, suppose we apply row interchange on the identity matrix and we get the elementary matrix E1. We call the elementary matrix E1. Then what is determinant E1? Pause and think about this. Ready? Can we use ABC to find out what determinant E1 is? If we use, which one will be useful here? A, B, or C? A says if we interchange two rows, then B determinant is minus determinant A. And now we have identity matrix here. We interchange two rows. The resulting matrix is E1. So determinant E1 would be determinant IN with a minus. And the determinant of IN is equal to 1. Because it's an upper triangular matrix, we can easily compute this determinant to be equal to 1, right? So this is equal to minus. How about this case? When we have identity matrix, we scale the ith row by C, and we have E2, elementary matrix. What is the determinant of E2? Which part of theorem 3.3 will be useful? We can use this B, right? Determinant E2 would be related to the determinant of identity matrix, like so. So we have equal to C. How about the last one? If we apply row addition on the identity matrix to get E3, what is determinant E3? Theorem 3.3 says when we apply row addition, the determinant remain the same. So we have determinant E3 equal to determinant IN equal to 1. Now let's consider the determinant of the product matrix E1A. How is it related to the determinant of A? Which part of theorem 3.3 can help us here? It would be A, right? When we apply row interchange, this is how determinants are related. And when we have the product E1A, it's the same as applying a row interchange, interchanging the ith row and the jth row. So we have this is equal to minus determinant A. Now, how is this related to the product of determinant? Determinant E1, determinant A. We already know what determinant E1 is, right? Determinant E1 is equal to minus 1. So this is equal. So for the first type of elementary row operation, we have determinant E1A equal to determinant E1, determinant A. So determinant of the product is the same as product of the determinant if the type of elementary row operation is the interchange. It's the type of doing row interchanges. Now, how about determinant of the product E2A? Determinant of the product E2A would be determinant of B matrix here, right? And the determinant B is equal to C determinant A. So this is equal to C determinant A. And how is the C determinant A related to this product here? We know determinant E2 here is equal to C. So this is C. So again, these two are the same. For the scaling type of elementary row operation, determinant of the product is equal to product of determinants. The last one, let's consider determinant E3A. Determinant E3A, the product E3A is the same as B matrix here. B is the result of apply the row addition, ERO on A, and determinant B is the same as determinant A. So this is the same as determinant A, and we know E3 has determinant equal to 1, so this is the same as determinant E3 and determinant A. So again, determinant of product is the same as product of determinant. Whenever E is an elementary matrix, whichever type it is, the row interchange type, the scaling, the row addition, the determinant of EA is the same as determinant E, determinant A. Now let's do the proof of A. Proof of A is the result on determinant when we do row interchanges of a row I and a row J. Let's consider first the simpler case that we do row interchanges of adjacent row I and the row I plus 1. Let's consider this a simple case first. So if we have A matrix here, this is A matrix, ith row entries are these red X, and the I plus 1 row entries are the blue one. Now we apply row interchanges of ith row and jth row. Then the blue one will go to the ith row, and the red entries will come to the I plus 1th row for B. Then what we know is that if we look at AIK element, this is the same as BI plus 1K. K goes from 1 to n. Determinant is defined using cofactor expansion, right? So let's call CMN be the cofactors of A and DMN be the cofactors of B. If we want to compute determinant and we do cofactor expansion along the ith row for matrix A, then naturally we will consider computing determinant of B using cofactor expansion along the I plus 1 row, because the elements in the I plus 1 row are the same as those here. So let's observe the connection of CIK and the DI plus 1K. These are the cofactors when we consider cofactor expansion along the ith row, and these are the cofactors when we consider cofactor expansions along I plus 1 row. How would they be related? For example, if we consider CI1, then we will cross out the ith row and the first column, right? And if we consider DI plus 1K, we would cross out this row and first column as well. Then how about the remaining submatrices? The remaining submatrices here, would it be the same as the remaining submatrices? They are exactly the same, aren't they? So when we consider the remaining submatrices here and the remaining submatrix, they are the same. So we should put, what should we put here? We should put plus. We should put equal, but then with an extra minus. Because remember, the cofactor carry the term minus 1 raised to the power I plus j. So here we have I plus k here, and minus 1 I plus k carry in the CIK term. And for D term, we would have minus 1 I plus 1k. There's an extra 1 here, so there's a minus here. So when we compute determinant B and we do cofactor expansion along the I plus 1th row, this is what we have. B I minus 1 1, D I minus 1 1, and then all the way to the nth element. For each cofactor D here, we can replace it by C minus Ci1 minus Ci2 minus Cin. And for each B, this element Bi minus 1, 1 is the same as Ai1, Ai2, all the way to Ain. And we see what this is, right? This is exactly the same as the determinant of A if we do cofactor expansion along the ith row, but then there's this extra minus sign here, extra minus sign. So we get minus determinant A. Now let's consider the more general case if we interchange row I and row J. We have already talked about interchanges of adjacent rows. Now, if we want to interchange row I and row J, is it possible to interchange these two rows using a series of interchanges of adjacent rows? That means that is it possible to interchange row I and row J by using interchanges of adjacent rows several times? As an example, let's look at this matrix. It has 4 rows, R1, R2, R3, R4. And suppose we want to interchange R1 and R3. What can we do? Can we do so by interchange adjacent rows? For example, we can interchange R1 and R2. Then R1 will come here, and then we can interchange R1 and R3 here again. But then R3 is now at the second row, and then we can do another interchange here. And then we can interchange R1 and R3, right? So indeed, it's possible. Alright, so if we want to interchange row I and row J, we can simply do interchange of adjacent rows a number of times, and for each interchange of adjacent row, there's an extra minus when we want to relate the determinant. Now, if we want to consider the general case, then we need to know how many interchanges of adjacent rows are needed if we want to interchange row I and row J. Pause and think about this. Suppose we have a matrix here. This is a matrix. And we have a row I here. Row I and row I minus I plus 1 all the way to row J. And let's say J is equal to I plus K. So their difference is K. And now, to interchange the red one and the green one, we can, for example, bring down the red one to the jth row first. So if we want to bring the ith row to the jth row, how many interchanges do we need? Every time we do one row interchange, adjacent row interchange, row I will come down by 1, right? And in order to bring it to the jth one, which is k rows away, how many interchanges do we need? We will need k interchanges. Now that we have ith row in the jth row position, now we need to bring the jth row to the ith row. In this case, how many interchanges do we need? Interchanges of adjacent row. Because this one is 1 row up to start with, right? Because now this jth row is occupied by Ri. So in order to bring it up to the ith row, we need 1 less, k minus 1 interchanges. Altogether, we need 2k minus 1 interchanges of adjacent rows. And remember, 1 interchange of adjacent rows means an extra minus 1. Now we have determinant B related to determinant A and a minus 1, 2k minus 1. So there we go. Determinant B is equal to minus determinant A. A question. Suppose we have an n by n matrix A, and the ith row of A is the same as the jth row. They are identical. What does this mean about determinant A? Pause and think about this. Ready? When the two rows are the same, that means in particular that if we interchange these two rows, then we still get the same matrix. When we interchange these two rows, the determinant from what we have just shown is related to determinant A by a minus, by an extra minus. But these two rows are the same, so we get the same matrix, so it's the same as determinant A. Determinant A is equal to minus determinant A. What does this say about determinant A? It could only mean one thing. Determinant A is equal to 0. Now let's consider proof for B. When we scale the ith row by C, then this is how determinants are related. When we scale the ith row, then B matrix will look like this. For the ith row of B, it will be C AI1, C AI2, all the way to C AIN. If we want to see how determinant A and determinant B are related, which row should we choose for cofactor expansion? The ith row seems to be a good idea. So we do cofactor expansion along the ith row. Then we get CI1 and the cofactor CI1. That's the same as that's because after we remove this one and this one, the remaining submatrix is exactly the same as the submatrix of A. So this is the same as cofactor of A, CI1. And we see that this is a C times determinant A. So that's the proof for B. And for those of you who are interested in the proof for C, for item C, you can look it up in the textbook. A question. Let's consider the determinant of the product E1, E2, and A. This E1 and E2 are elementary matrices. They may not be the same as E1, E2 here. This E1 corresponds to the elementary row operation of row interchanges, and this E2 corresponds to elementary row operation of the scaling. But here E1, E2 are simply elementary matrices. They are not necessarily the same as E1, E2 here. How would this determinant E1, E2A related to this one here? Determinant E1, determinant E2, and then determinant A. To consider this one, we can simply look at it as E1 and then the product E2A. Then we can pull out determinant E1 and then determinant E2A. And this is the same as the product of determinants. Determinant E1, determinant E2, and determinant A. This is true for any elementary matrices, E1, E2. Now let's use what we have learned here on Gaussian elimination. Remember, in Gaussian elimination, we apply a series of elementary row operation, and in step 1 to 4, we have this forward pass, and in forward pass we use row interchanges and we do row additions, and we arrive at we arrive at row echelon form, not reduced row echelon form, just row echelon form. And this row echelon form is a upper triangular matrix. And we obtain U using a series of elementary row operations. So U can be written as ek minus 1 to ek A for some elementary matrices. This EI matrix corresponds to row interchange or row addition, because in step 1 to 4 we use only row interchanges and row addition. And remember, when we apply row interchange, there's the connection between determinant. There's this extra minus 1 when we consider determinants. And when we apply row addition, there's no change in determinant. So determinant U and determinant A now has the very nice relation. Determinant U is determinant A with the extra, minus 1 J0. J0 is the number of row interchanges. Or we can say determinant A is equal to this one. And what's the use of this? We want to compute determinant A, right? And this relation now gives us an alternative way to compute the determinant A. Remember how we define determinant A? We use cofactor expansion to define determinant A. So we need to compute determinant by expanding along a certain row, and then we get smaller submatrix, and then for the smaller submatrix we can again expand along a certain row to get determinant of an even smaller submatrix, continuing on iteratively. But now with this relation we can compute determinant in this way. We can do Gaussian elimination, and we do only the forward pass to get the upper triangular matrix raw echelon form. And because this raw echelon form is upper triangular, whose determinant is very easy to compute. It's simply the product of diagonal element, and the determinant A can be computed this way. Determinant A is equal to minus 1 J0, U11, U22 all the way to UNN. For example, this is the A matrix, and we apply Gaussian elimination, the forward pass, to bring it to the raw echelon form, an upper triangular matrix. And to get this raw echelon form, we have applied two interchanges and some raw additions as well, but because raw additions does not change the determinant, so we don't count them here. The determinant of this upper triangular matrix is minus 1, 1, 4, 1, the product of these four entries. And we do two interchanges, so we get a minus 1 square. So we can get determinant A equal to minus 8.